We've already learned that a charged particle moving through a magnetic field can experience a magnetic force. In this video, we're going to focus on a whole bunch of charged particles moving in the same direction, otherwise known as a current traveling through a wire. Let's think about this for a moment. We know that current is the motion of charged particles. And so if we put a wire with a current in a magnetic field, it would then make sense that each of those charged particles moving through the field would experience a magnetic force, meaning that the whole wire would also experience a magnetic force. Let's start out by focusing on a single charged particle that moves in this magnetic field. We know a single charged particle moving in a magnetic field experiences a magnetic force according to the equation FB equals QV cross B. Now, we also happen to know that current I is equal to the rate at which charges are moving through a wire, or dq dt. And if current is constant, it can be expressed as delta Q over delta T. So let's solve this last equation here, the delta Q, for our charge. Delta Q equals I times the change in time. And let's say once again we're focusing on a single particle. I'm going to plug that into my magnetic force equation so that my magnetic force, FB, is equal to I times time times velocity cross magnetic field. Now, we happen to know from what we've learned previously that when I multiply time times a velocity, I end up with a distance. Let's say in this case we're talking about the distance that electron travels in the wire, otherwise known as L. I can then find an expression for the magnetic force on the wire rather than the magnetic force on an individual particle. Notice in this case that L is the quantity that is treated as a vector. L has the same direction as velocity, or the velocity of a positively charged particle, to be more specific. Now, we know technically that current is the thing that has a direction, the thing we're used to having a direction, and current is the direction of a positively charged particle moves. So, in this expression for the magnetic field, or magnetic force rather, on a current carrying wire, the L, which is our vector, points in the same direction as the current that travels through that wire. As you can see in my diagram here, if I have a magnetic field that's pointed out of the screen and the current traveling up through the wire, that wire would experience a magnetic force pointed to the right, which can be determined from the right-hand rule. Also, if I have a same magnetic field pointed outward, but the current is traveling downward, the magnetic force points left. We can use this equation, similar to our equation for magnetic force on a charged particle, to calculate that force. And also similarly, that force is always perpendicular to the length vector and the magnetic field vector. We'll do some practice with this in class.